Welcome to the fourth installment of Oak Ridge National Laboratory's Invention to Innovation webinar series. My name is Jennifer Caldwell, and I am the group leader for commercialization at ORNL. Today I will provide you with an overview of our IP portfolio for the areas of energy, utilities, and transportation. I will then invite Dr. Mariappan Paranthaman, a distinguished research scientist and group leader for materials chemistry at ORNL, to present our featured technology, a low-cost carbon black composite for battery anodes. During today's webinar, you can text or email questions to ttpd@ornl.gov, and we will answer these questions at the end of the webinar. In 1943, Clinton Laboratories was established in Oak Ridge, Tennessee, as part of the World War II Manhattan Project, to develop the first atomic weapons. The plutonium production methods that were used at Hanford were piloted here at Clinton Laboratories, and the facility was renamed Oak Ridge National Laboratory in 1948. Today, Oak Ridge National Laboratory is the largest science and energy national laboratory in the Department of Energy system. Our scientific programs focus on materials, neutron science, energy, high-performance computing, systems biology, and national security. This slide shows an aerial photo of the main campus of ORNL, and as you can see, the lab has benefited from significant modernization to provide a university-like atmosphere. We have a $1.4 billion annual budget funded by the Department of Energy and other federal agencies, such as the Department of Defense, the Department of Homeland Security, NASA, and the Nuclear Regulatory Commission. We have 4,400 employees and 3,000 visiting researchers. In addition to our scientific program in energy and security, we also house facilities such as a supercomputer that is currently the most powerful open computing facility, the Spallation neutron source with the world's most intense neutron source, and a world-class research reactor. ORNL researchers engage with the private sector to bring lab innovations to the marketplace. This year, we received 8 R&D 100 awards, bringing our total up to 187. Our guest speaker today has received 4 of these awards at ORNL. Our R&D innovations often include intellectual property, providing a diverse IP portfolio with over 800 inventions in areas included on this chart. We have already highlighted a few of these areas in previous webinars, such as detectors and sensors, analytical instrumentation, manufacturing, materials, and chemicals. Today, we will focus on the area with the largest presence of IP, energy and utilities, and transportation. This portfolio covers a variety of topics, including those shown on this slide. Any one of these topics has many inventions and copyrights within it. For example, in the area of energy storage, our researchers are working on important innovations such as battery technologies including novel anodes, shown here, cathodes, new electrolytes, as well as energy storage systems. And ORNL facilities important to energy storage are also available to not only our scientists, but also the private sector. These include the Battery Manufacturing Facility and the Center of Nanophase Material Sciences Facility, where characterization of battery materials can be conducted. Today's webinar will focus on an exciting opportunity that we have that develops a carbon black composite for batteries. We are now encouraging the private sector to partner with us and bring this technology to the marketplace, and this licensing opportunity is announced on FedBizOps. Here's the information to guide you to learn more about this solicitation. We look forward to partnering with the private sector and know that industrial collaboration is critical for the lab's R&D to make it to the marketplace. We believe that the private sector will also benefit from working with the National Laboratory. A national laboratory has unique and strong expertise and capabilities that are typically not found elsewhere. Our state-of-the-art facilities are a reliable resource with sustained DOE commitment. And many companies find that engaging a national laboratory in a multi-year collaboration provides a great benefit as the lab works with you on long-term challenges. Industrial partners translate the lab's R&D into market impact and support for U.S. competitiveness. How can the private sector partner with a national laboratory? We have 4 specific mechanisms that will allow you to tap into our expertise and capabilities. User agreements allow you to be able to access or use our facilities. Cooperative research and development agreements, known as CRADAs, and work for others, allows you to work with our researchers. And intellectual property licenses allows rights for you to obtain for our IP in order to commercialize ORNL technologies. The bottom of this slide shows the volume of transactions for all the DOE laboratories in 2013. As you can see, labs partner often with the private sector to bring our inventions and innovations to the marketplace. I will now step through each of these mechanisms and briefly describe the benefits to you and also summarize the intellectual property terms common to the agreements. Our user agreements are needed for users who are selected to use our user facilities. Users that agree to publish the results of the project can use the facility free of charge. And users who do not want to publish the results can use the facility as a proprietary user. And they must also provide full cost recovery for their use of the facility as a proprietary user. In the case of a proprietary user, all inventions arising during the project are owned by the sponsor or the user, whereas inventions arising under a non-proprietary user agreement are owned by the parties inventing the IP. CRADAs cover work where the private sector is collaborating with the laboratory. In some cases, the work under the CRADA performed at the laboratory may overlap with existing projects funded by a federal agency and will require the CRADA sponsor to only fund their efforts under the CRADA. In other cases, the project in the CRADA may not overlap with an existing funded project at the laboratory and would require the sponsor to fund the effort at the laboratory along with their own efforts. Regardless of the funding arrangements, the intellectual property is handled as follows. Each party owns its own inventions that were created during the course of the CRADA. Sponsors are granted field of use exclusive options to the laboratory-owned inventions and copyrights created under the CRADA. No rights are granted to background IP. Generated information that is not patentable can be kept confidential as protected CRADA information for up to 5 years. Work for others allows the private sector to pay for work to be completed at the laboratory. This work usually requires some unique capability or expertise that is needed by the company. The work is fully funded by the sponsoring company, and in general, the private U.S. sponsor, using private funds, will own any intellectual property, such as inventions and copyrights, that arise during the Work for Others project. We are also able to partner with companies through the transfer of our own inventions and copyrights under IP license agreements. We can enter into both exclusive and non-exclusive licenses in specific fields of use. Exclusive licenses require substantially manufacturing of licensed products in the U.S., and non-exclusive licenses require a U.S. benefit both economically and technically. Information about all our inventions and copyrights are available on our ORNL Partnerships website. We look forward to discussing the opportunities that meet your market interests and industrial needs. Today, our featured presentation highlights an exciting ORNL opportunity. Dr. Mariappan Paranthaman will join me to present an overview of a low-cost graphite anode for lithium ion batteries. Dr. Paranthaman began his work in energy storage at the University of Texas with Professor John Goodenough. He has a strong track record in bringing technologies to the marketplace in the areas of superconductivity, solar technologies, and now again in energy storage. He has provided ORNL with exciting research since he joined the lab in 1993, and it is my pleasure to invite him to present his technology to you today.
Thank you, Jennifer. Good afternoon, everybody. And I'm very pleased to talk about a new commercial opportunity to you. So I'm going to, as you can see the slides, low-cost graphite anodes for lithium ion batteries. I'm the PI for this project, and licensing contact, you can do Jennifer Caldwell, and her phone number and email are addressed. So let's look at the commercial opportunity what we have. As you can see on the top right-hand side, we have a pile of recycled tires available. And mainly wound rubber tires were sent to landfill in the past. If you look at in 2003 EPA website, nearly 290 million scrap tires were generated in the United States. And 80% of those waste tires were used in applications for fuel, as additives in civil engineering applications, as fillers in plastics, rubber, asphalt, and various applications. If you take a tire, like typically they add 40% carbon black and metal oxides are added to vulcanized tires to improve the tensile strength and resistance to swelling and abrasion, and are elastic over a greater range of temperature. So I'm going to talk about the methodology we developed at Oak Ridge to recover carbon black composites from recycled tires, and demonstrated its use as anodes for lithium ion batteries with increased power and energy density. And there are other uses like of this graphite include sodium ion batteries, fuel cells, and supercapacitors. So the commercial opportunity, we have a great opportunity to be the leader in low-cost graphite anode materials supplier, or as a lithium ion battery cell manufacturer. So let's look at the technology description. So this is a low-cost graphite anodes. So if you take recycled tires, so you can shred it and pulverize it into tire powders, and you can pyrolyze, and you just heat it to get black powders. That we call it as a control tire rubber derived carbon. This is a controlled sample. You just take the powders, heat it, and recover the powder. And what we did was we made them as anodes in a coin cell configuration for batteries. And what we have developed is we have introduced a method, acid treatment method, mainly the sulphonated method. So what we have is you just take the shredded powders, you go through the acid treatment and pyrolyze it. It's like a two-step process. You shred it, go through the acid treatment and pyrolyze it, and recover the carbon black. So what we call is sulphonated tire rubber derived carbon. So we have two technologies, and we made them in the form of coin cells and tested the properties for lithium ion batteries. So the technology readiness level, TRL, that's very critical for commercialization. So we are currently in 3. So what we want to do is from 3, we are in the process of making like large format cells, pouch cells, so that we can be in 4. So if we can work with you, we can take it to the marketplace in 2 to 3 years, 5 to 6, and we have filed a patent based on this technology, and we have the IP covered. So I'm going to talk about the technology opportunity for our case. So what I'm comparing is 2 kinds of carbon. One, the standard controlled tire rubber derived carbon, where you saw the taking the powders, pyrolyzing and recovering the powders. The other one is sulphonated tire rubber derived carbon. So that's the method we developed at Oak Ridge. So let's look at the microstructure and the properties. So this is a carbon controlled tire rubber derived powder. So the morphology, as you can see the TM image on the left, the fluffy low density carbon with irregular shape. So we have 8 to 13 nanometer pore size. The surface area is like 96 meters square per gram, and they are completely amorphous as per the selected area diffraction pattern you can see on the right. So let's compare with the sulphonated tire rubber derived powders, and it has more like a hard carbon monolith with a one-dimensional nanostructure, and they are 3 to 4 nanometer pore size and low pore volume. And this has a surface area of 64 meters square per gram, and you can see in the selected area diffraction pattern, both crystalline and amorphous phases are present compared to our control sample. The end product is carbon black containing product comprising a glassy carbon matrix phase having carbon black dispersed in them. So that's the end product what we have when you go through the sulfonation followed by pyrolysis process. So what I'm going to show is both this control and the sulphonated tire-derived powders were tested for battery applications, and we are also comparing these results with a commercial graphite. That's what we are comparing in a lithium-ion battery. So before we get into the results, let's see what is a lithium-ion battery. So this is a schematic. So this is a secondary ion battery. So we have two solid electrodes, like we have anodes and cathodes. Anodes are typically the graphite, and the cathodes are lithium containing oxides like lithium cobalt oxide, lithium manganese nickel oxide, or lithium iron phosphate. And the electrolytes are liquid electrolyte. We have dissolved like 1 molar lithium hexafluorophosphate in ethylene carbonate and diethyl carbonate solution. So this is the electrolyte, liquid electrolyte. So when you do the charging, what happens is lithium comes out of the cathode from the lithium cobalt oxide, as you can see in the equation on the cathode. So the lithium goes through the electrolyte and intercalated into the anode, into the layered structure. So you are transporting lithium during charging from the cathode through the electrolyte to the anode. To compensate this reaction, electrons go through the external circuit. So during discharging your battery, lithium-ion batteries, you are reversing the reaction to opposite. So the net reaction is we use a graphite and lithium cobalt oxide, and this is a reaction we have. That's what you have typically in iPhones and cell phones and all these iPads and laptops, all the batteries. So let's look at the battery performance of commercial graphite powder. This is the commercially available sample, something we made coin cell. So the battery architecture, we have carbon and lithium. This is a half cell configuration with the electrolyte, and we made coin cells. And I'm going to talk about 1C. 1C means one charge discharge cycle in an hour. Like how long will it take to charge and discharge in an hour, 1C. So I have plotted the cycling performance of these batteries, the commercial graphite, at 0.1C, okay, 1/10 of a charge discharge. So you can see the plot, both right side is the Coulombic efficiency and the bottom both charge discharge, and the capacities are close to like 350 to 360 milliamp hour per gram. After 2 cycles, the capacity comes down because of the reaction between the anode and the electrolyte, solid electrolyte interface. So you do see a small drop. Then it's pretty constant over like 40 cycles we have shown. And this is a commercial graphite. And if you look at the first and second charge discharge curves at 0.1C, you can see the voltage drop, and the first capacity is a little higher, and the second one is, you can see it drops from the first to second. And if you look at the microstructure, both this diffraction, amorphous, and crystalline phases are present, and this is the morphology. So these are commercially available graphite, something we tested, and it gave like 350 milliamp hour per gram. And also if you do the rate performance, like different thing, you couldn't go to very high rates. That means you can't do fast charging using some of these commercial graphite, and I'll show some data with the sulphonated batteries. So let's look at the controlled tire rubber derived graphite. So what I'm talking right now is the one I talked about. You take the powders, you just go through the pyrolysis and make the graphite, and you get, that's what you have. So you can look at the cycling performance at 0.1C. The capacity after few cycles, it goes down. It saturates, you can see the red and blue, both charge discharge curves, and it's plateau, but you have only 200 milliamp hour per gram. So we saw in the case of commercial graphite over 350 to 360, the theoretical limit for graphite is 372 milliamp hour per gram. Whereas here, it's 200. And if you look at the same thing, first and second charge discharge curves at 0.1C, so we have a huge drop, and that means you have a reaction between the anode and the electrolyte. And if you look at the rate performance, like you can see the capacities at 2C and 5C is really low capacity. So you couldn't use this control sample. And to summarize this material, controlled tire-derived graphite capacities, I would say like 200 milliamp hour per gram after 45 cycles. So let's look at what we have with sulphonated tire rubber derived graphite. So this is the extra step what we developed at Oak Ridge, go through the acid treatment and then pyrolyze and make the graphite powder. It's the same half cell configuration. And if you look at the performance, the Coulombic efficiency, the green one is you need to be close to 100, so we are very close to 99.9. And the discharge capacity, you can see the first capacity is high, then it drops down to like 390 to 400 range, and it's constant over 100 cycles. So we have shown a performance of our sulfonated tire-derived graphite for 100 cycles in the coin cell configuration. So you can see it also the first, second charge discharge curves, and you can see again the voltage drop is also, I'll talk about it in the next few view graphs, and capacity drops after few, but it's holding steady. And the rate performance, if you look at 5C, like we have done it at different Cs, 5C and also 10C, the capacities are still high. So there is an opportunity for this sulfonated tire-derived graphite, you can run it at slightly higher capacity. To summarize this technology, the sulfonated tire rubber derived graphite has 400 milliamp hour per gram after 100 cycles. So we have shown the technology is either equal or better than the commercial graphite, the sulfonated opportunity. And we have demonstrated a pathway for making high performance carbon materials from the waste tire products for their potential use in energy storage applications. So we are really taking something you throw away when you change your tires to take it in the marketplace for energy storage applications. So we wanted to confirm this data independently in another lab. So Sandia lab, that's where people send the batteries for testing, and we have worked with them to test, compare both commercial graphite with the ORNL sulfonated graphite. So what they did was they took their standard commercial G8 carbon with a capacity, and they achieved. So we have plotted voltage versus time, and one good thing is the capacity is 320 milliamp hour per gram, but sharp voltage response with time. One thing what I heard is these commercial graphites have particle size like 10 microns, is really uniform, and this is a commercial sample. So this is the commercial graphite. Let's see how the ORNL sulfonated tire rubber derived graphite performed. And this is again in a half cell configuration, and they achieved 340. And if you look at the voltage performance, here there's a slow voltage drop compared to the large. This could be either the large size of the particle or something intrinsic, because I said it's forming some composites more in the form of mesoporous. So we are still working on, and this is an issue, something we want to make it change, because our particles were too large, and we found a method. I am going to talk about how we can grind it and get to the small particles. And but however, this sulfonated tire carbon outperformed the standard G8 carbon. So the capacities are good. So we have independently confirmed the battery performance at Sandia. So let's see, can we take it to a large scale? So what we have done is so far like 80 to 100 gram batches of graphite powders with a mean particle size of 3 microns through grinding and sieving. So we already made these powders. So what we do is after pyrolyzing, you go through the smell grinding, and you get initially like 10 microns. We have done final grinding and sieving, and you can see on the bottom the particle size. You have two model particle size. If one wants to sell these powders, so you can give the specifications of the particles in two different ranges. So this is a mean size of 3 micron size. So these are really good. We can make it. And in addition to sending batteries or testing at Sandia, so we are also working with our scientists at the battery manufacturing facility at Oak Ridge. So they have taken some of this sulfonated tire rubber derived graphite, and they have made coatings on large. You can see copper anode as the metal contact for anodes. So these are carbon graphite coated graphite copper substrates. And they have also made single unit pouch cells. So these are single. So what we have done is going from half cell configuration to the full cell configuration in the pouch cell. So the cathodes are NMC 532. These are lithium, nickel, manganese, cobalt oxide, and the anode is a sulfonated type. separator, electrolyte, and the standard conditions. So we have already made some cells, and we are in the process of aging and testing are underway. So I have shown you like how we can take these powders, separate it from the tires, and how we shown the performance in coin cells. So let's look at the competitive differentiation between our technology and the technology that's known outside. So I have a table. So I am comparing the technology feature like battery performance, cost, long cycle life, rate capability, and scalability. And the ORNL technology is the one, the first column is the one I talked about today. We are comparing it with graphite from petroleum coke, that's a standard process, or mesoporous carbon, it's a lot of literature known, and also carbon from polymer sources or other sources, plastics. So the battery performance are comparable, I would say, to graphite or any polymer source. However, mesoporous carbon may have higher performance than this standard graphite, but the cost-wise, we are going to be the cheapest compared to any technology that's known right now with respect to graphite powders for battery electrode materials. And long cycle life, we have shown like 100 cycles of these batteries made out of sulphonated tire-derived powders. And the rate capabilities, I showed just like the mesoporous carbon, some of these graphite powders, and you can electrode batteries, you can run it at high charge rates like 5 Cs and 10 Cs. And the scalability, we have done like up to 100 gram batches, but if you really want to scale up, so you can have a large drum, and 100 tires would weigh like typically 1 ton. So you can take these 100 tires, shred it into pieces, soak it in the acid in a drum, and you go through a pyrolysis, and you can get these carbon powders. And we get up to 45% yield of the starting material. So that's what we recover in the case of, so we can scale up. So the other thing we need to look at is, in addition to performance and cost, both I showed, this ORNL technology has its advantage of societal, economic, and environmental benefits. You don't want to leave the tires piled up so long, can catch fire. So we have a lot of environmental benefits. And we have unlimited source. This is a low capital cost. And we have demonstrated a green energy of waste to energy storage conversion. This is a great opportunity for you to look at very close. So let's look at the estimated battery cost analysis and market opportunity. So I'm just comparing the pie chart of Argonne National Labs estimation for 100 amp hour high energy cell. So this is, you have cathode, graphite, electrolyte, and separator. Graphite is about 11 to 15% contribution. The cost of materials for high energy cell today, it can cost up to $400 or more per kilowatt hour, because that's what we care. If you want to buy your Tesla cars or any EV car, you are going to compare the cost of the battery, because we need to reduce. So if you look at the Duke University thesis report a few years ago, so you can see the battery cost has to really come down. For all this PHEV, either hybrid vehicle or EV vehicle, you need to be in the range of $200 to $300 per kilowatt hour to penetrate the market, so that you can dominate using the lithium ion battery for the automobile applications. So you need to have reduce the cost. That's a key thing for the Department of Energy to work on. The global, let's look at the battery market. It's over 77 billion. It's almost $78 billion battery market in 2020 estimated. And the global battery materials market is almost over 11 billion in 2018. So we have a great opportunity to use our technology for batteries. So let's look at the market opportunity. This is a one Roscal estimate from 2012. The global graphite demand, so we use like 32% of electrodes. As I told you, graphite can be used in refractories and other things. So you can see the variety of applications for this graphite. So around 80% of the graphite used in batteries mostly consumed in lithium ion batteries in 2012. The estimated graphite consumption in batteries is going to increase to 114,000 tons by 2016. 114,000 tons we need graphite for 2016. Mainly what's happening is all these hybrid vehicles and the electric vehicles slowly moving from the nickel metal hydride batteries to lithium ion battery. So there is a big market shift is happening. So if you take a typical Nissan Leaf EV car right now, it has 40 kilograms of graphite. Just for one car, you need 40 kilograms of graphite powders you need for the batteries. So the estimated graphite market is like $12 billion. At least 10% of the battery market is likely to be captured using this. The other thing what's happening is due to the graphite demand, the cost has gone up 3 times over the last 4 years. And the graphite cost can range from $5 to $20 per kilogram. However, high quality graphite you have to pay $60 per kilogram. And I have plotted the bar chart of the current global production of graphite. You can see different sources, synthetic, all these different kinds of carbon. 3 million tons of graphites are produced worldwide. 3 million tons of graphites are produced. So out of which we need 114,000 tons of graphite for batteries. So next step, what we want to do. So using our internal funding, technology transfer funding, our goal is to scale up the technology. So we want to show so that we can take it to the pouch cells, something so that it's reproducible to show whether we can scale up. That the goal is to develop a low-cost, scalable carbon black composites from recycled products and demonstrate its use in lithium-ion batteries. The task is we want to scale up with a tailored microstructure, something I showed so that you can improve the performance. Either it's comparable or better than the commercial graphite. So you have to tailor the microstructure. And also you have to optimize the conditions, because I said like you have a soaking time, so there are optimization involved. How long can you soak it and what kind of acids, and also the pyrolysis temperature and time, residence time. So those are variables. So we need to kind of optimize those conditions for scale up, and we are still in the process. And the task 2 is we want to demonstrate these batteries in the form of fully charged high energy density battery and also full cell configuration. And we are working with both Sandia National Lab and also Oak Ridge Battery Manufacturing Facility, and we use a standard cathodes and electrolyte standard. Everything, we are just replacing the commercial graphite in a large format cell with the sulphonated tire-derived graphite powders. So we want to work with industry partners so that we can demonstrate and go to the phase 2. That's what we are interested in working with you. And let's look at the applications and the target customers and current practice. So the major uses of graphites are in batteries, fuel cells, and supercapacitors. So you can use them in various energy storage applications. So if you look at like lithium-ion battery, anode is a host material for lithium intercalation, and the types of graphite used are primary synthetic and spheroidal flake graphite. In the primary alkaline batteries, you can use again graphite in the cathode as additives. For lead acid battery, typically we use in our cars every day to start our car, and they use graphite as additives in both anodes and cathode. Again, you can see all these different forms of graphite used. And in fuel cells, you can use bipolar plates and mainly as filler material. So you can use them as, and the target applications are you can use in automobiles or mobile devices, and the target customers are EV car manufacturer or hybrid car manufacturer, like current practice like GM, Ford, Nissan, and Toyota. They are all already using it. And the stationary storage, you do want to, and medical use, you can use these batteries and battery cell companies. And now we are mostly importing these batteries from Japan, Korea, and China, and mainly Asia. And we can also use these batteries in military applications, and mainly target customers are battery cell companies, and we are again importing from Asia. So I would like to thank and the sponsor acknowledgement, like sponsored by UT Battelle, our technology innovation program, and also internal LDRD funding, and Office of Basic Energy Sciences, Department of Energy, Materials Science and Engineering Division for sponsoring some of the work we did from the technology, from the battery fabrication to characterization. And the research are supported by my colleagues. Amit Naskar at Oak Ridge is the original inventor of extracting this graphite from the recycled tires. And I would like to thank my colleagues like Craig Bridges, Sam Akato, Yanchao Lee, Mia Feng Chi, Janlin Lee, David Wood at Oak Ridge for help in synthesizing and scaling up and testing some of these batteries. I would like to thank my friend also, Dr. Nagasubramanian at Sandia, for testing some of our batteries in both coin cells. And the contact information, you can see both my phone number and email address, and Jennifer Caldwell's phone and the email. And the webinar schedule, we have two upcoming webinar schedule for September 3rd and September 24th. And I'll be happy to answer any questions you have. And ORNL is, as to summarize, it's a science and technology for innovation. And I'll be happy to answer any questions. And thank you.
So Paranj, we have a couple of questions from the web. The first is, what is the mean particle size of the starting material you use to generate the pyrolytic carbon black?
Typically, these particles are maybe like 100 to 150 micron size, I would say. That's a starting powders, yes.
And was this material cryogenically generated, or was it an ambient powder?
These are cryogenically pulverized and powders, yes.
Second question, looking at the costs, can you compare the cost of the powder that you're producing with commercial graphite powder?
Okay, so let's, I think I have something about the cost of the graphites we had somewhere. So it I think it will cost like it can $5 to $60 depending on the use. So if you need high quality graphite, maybe this one. Okay. Oh, sorry, it went to the first. Okay, so it can cost $5 to $60 per kilogram. Whereas when you want to change tires, actually you are paying. You have to pay couple of dollars to get rid of your tires. So you are paying to get rid of, the customers are paying. So we can get the tires for free. Then when you go through this process, we strongly believe we can make like somewhere in the process, depending on the scale of, few dollars per kilogram, I would say. That's the estimate.
And this few dollars per kilogram powder, is that comparable to the $60 per kilogram powder?
Yes.
Okay.
Yeah. The performance-wise, it's definitely. And there are some challenges involved, but we will go through it, yeah.
And what level have you scaled your production system to date for the composite
As
graphite?
I mentioned it during my presentation, so we have done like 100-gram batches right now so far. We have gone from 10 grams to 100 grams batches, but I don't see a showstopper. And like I said, 100 tires will weigh like 1 ton. So you should be able to run like 1 ton batches in a drum, go through this both acid treatment and pyrolysis.
And the last question we have is, what are the waste products from your production system, and are these different from what would normally be found in the industry?
That's a very good question. I mentioned briefly, it's only 45% yield. So we are recovering carbon black composites from the tires. Still, we have 50% waste. And when you have sulfur, that's an issue, okay. But when you're doing recycling, you can always remove sulfur out of this waste product. Then you can convert sulfur to sulfuric acid. Then you can actually use the sulfuric acid. I just recently heard there's a Belgium company. They are recycling mainly hard drives, and they go through this process in a large scale. They take this sulfur, they take it out, not from the graphite tires, but from the circuit boards and other things, and they convert them to sulfuric acid. You can use it for etching. So we can convert usable product, acid from the sulfide. And also we need to worry about higher hydrocarbons. So you could use like scrubbers for controlling some of the higher hydrocarbons during pyrolysis, because we have to work closely with EPA so that we can be in compliance with our process.
Well, Paranj, Jennifer, thank you very much. This concludes our webinar, and we look forward to seeing everybody again in a few weeks. Thank you.
Thank you.